Welcome back. This is our first assignment for semester 2. We're going to review some of the key points from semester 1. So let's make sure that you're taking notes carefully. So a key point here, just because the first derivative is equal to 0, of course that means that f has a horizontal tangent, but does a horizontal tangent always mean extrema? No, think of x cubed. We know that at the origin the first derivative is horizontal, and it could just be what we've been calling a saddle point. So there's your counterexample. In question 4, the question isn't whether there's continuity, it is whether there is a limit. So all we have to check is, does the left-hand limit as x approaches 1 from the left side equal the right-hand limit? So there could be a pop point, which would mean that there's no continuity, but that's not the question. Does the limit exist? So all we need to do here is find the left-hand limit. So what happens if we put 1 into the left-hand function? And we will get 2. And then we find the right-hand limit. What happens if we put 1 in? And we will get 2. So indeed we can see the value of 3 will be a pop point, but we're not asked about that. Does the limit exist? Yes, it does. And in 14, you were tricked by this. The fact that the second derivative is 0 does not prove inflection point. It only has an inflection point if f double prime changes sign. So if f double prime of x changes sign at x equals c. So our counterexample was f of x equals x to the fourth, which is concave up. So the second derivative at the origin will be equal to 0, but it's a double root. So the fact that f double prime hits 0 is not enough. And 16 is actually our definition for, or our theorem for chain rule. We have f composite g, that's the definition of h. So this is wrong. Our composite rule says that we take the derivative of the outer function, but we leave the inner function alone, and then we multiply by the derivative of the inner function. So 16 is not the correct chain rule. 21, don't get tricked by this again. It's going to keep showing up here. Think of your algebra. We know here that we're going to do the x squared first. It's going to become positive. So when we do the square root of x squared, we get absolute value of x. So when x goes to negative infinity, our numerator will be negative 3 times infinity, but our denominator will be positive. So it does not go to 3, it goes to negative 3. 25, I hope you recognize this as our definition of a derivative. So here's our f of x plus h minus f of x. So all we're being asked for here is f prime of x when x is equal to 2. So we don't have to do the algebraic method because we can just use the power rule. So we'll have negative 16x to the negative 3. Which of course is negative 16 over x cubed. Put 2 in there, and we very simply have an answer of negative 2. In 27, the derivative of e to a glob is not e to the glob, it is e to the glob with a chain rule on the glob. So make sure you never forget a chain rule. 29 is a pretty basic formula. Got to memorize those formulas. The derivative of log of x is 1 over x times the natural log of the base. There would still be a chain rule, by the way, but our derivative of x is just 1, so we don't need a chain rule here. 43 is a bit of a trick. There's no variable here. This is a constant. So the natural log of e squared, you guys, those are inverses. That's the same as saying g of x is equal to 2. Remember, you could bring the exponent down in front of the log. So the derivative of a constant is 0, as opposed to 44, where we do have a variable. So in 44, the derivative of natural log is 1 over the glob times the chain rule on the glob. And then we can clean this up by factoring. So we'll come up with a 2 over x. In 48, two different ways to do this, of course, a long and a short way. The short way is to realize we don't actually have to use the product rule because we could divide and make this an explicit function. So this is the same as y is equal to 8x to the negative 1. So we could do the first derivative by the power rule. Let me make that a negative 8. And then we could do the second derivative again by the power rule. So this is like the problem we just did a minute ago. And then we want to evaluate this at the point where x is negative 2. So not much different than we just did a minute ago. So I think we'll, if my signs are correct here, did I lose a sign? I think I'm okay. So we should come up with negative 2. Let's try that using the product rule method. Using the product rule, so starting over again from scratch, we would have the first times the derivative of y would be 1, y prime as the chain rule, plus y times the derivative of the first term x, which is just 1, equals the derivative of 8 would be 0. So here I could move the y to the other side and divide by x. And then for our y double prime, we would do a quotient rule. So we'll have a low, that should be an x there, a low d high, the derivative of y is y prime, minus high d low, the derivative of x is just 1. And if we replace our y prime here, if we replace y prime with what we just found a minute ago, that could be replaced with our negative y over x term. So let me rewrite this here. If I replace that y prime with what we just found out a minute ago, then look what's going to happen. These x's will cancel, and here we'll have, let me just be a little careful here. This negative sign, remember, is out in front of the whole fraction. So let's be careful about that negative sign. So it distributes times each of these terms. So we'll have a positive y and a positive y. So we've got a 2y over x squared. So now let's evaluate this formula at negative 2, negative 4. And we'll come up with a negative 8. And a negative 2 squared in the denominator will be a positive 4. So again, we've got our answer of negative 2, whether you did the product rule method or whether you did explicit differentiation. All right, question 49 is, do you know the second derivative test? So we've got a polynomial function, so we know it's continuous and differentiable everywhere. Its derivative exists. At 7, it happens to have a derivative of 0, so that means that f has a horizontal tangent. And the second derivative at 7 is positive 1, so that tells us that f is concave up at that point. So remember our little shape here? If we have a horizontal tangent in a concave up section, then we must be at a local minimum. So the answer that fills in the blank here is local minimum. It could be a global minimum, but of course we don't have enough information for that. All right. How about derivative of cotangent squared? So remember that that exponent is on the outside. So our chain rule, first we would do the power rule. We would reduce that exponent to a 1. And then we would do the chain rule on cotangent would be a negative cosecant squared of x. And yes, sadly, you are expected to remember your unit circle. So at pi over 4, I think too many students are hooked on this rationalized version, radical 2 over 2. Perfectly fine, but remember where that came from. That's 1 over the square root of 2. The reason I prefer this is, look at if we have to do cosecant. Cosecant is the reciprocal of y. So isn't it much easier to flip this one over and then we don't have to rationalize again? So what I mean by that is that cosecant of pi over 4 is going to be square root of 2. And the cotangent, of course, just like tangent, the legs are equal, so the ratio of x to y is the same as y to x. So here we'll have a 2 times a negative 2. So a negative 4. So sadly, I bet the trig was as much a cause of problems as the calculus. How do we prove a cusp? What's the definition of a cusp? Well, let's draw a seagull here. And the idea of a cusp is at this C value, notice that the slopes have to go to a negative infinity on one side, and the slopes have to go to a positive infinity on the other side, or vice versa. You could have the seagull flying upside down. So what we would need here is if the derivatives go to infinity or the slopes go vertical. So what we would need here from the left side in this diagram, the derivative would be going to negative infinity. And for this diagram on the right-hand side, as we come from C from the right-hand side, the derivative or the slope of the tangent lines are positive infinity. And of course, you could reverse that. So it could be the other way around. The limit from the left-hand side, if our seagull was flying upside down like this, from the left-hand side, the derivative could be positive infinity, and from the right-hand side. So you could say vice versa if you don't want to rewrite this. And I think you would be given credit. So there's our definition of a cusp. The tangent goes vertical from both sides. All right, and here we have motion along a straight line. So when is speed decreasing? Speed decreases when acceleration and velocity have opposite signs. Remember that if I push you in the direction you're already going, then you would speed up. If velocity and acceleration have opposite signs, then you would slow down. So you can slow down whether you're going forward or backwards. So let's see what we know here. The derivative of position is velocity. So here we'll have 6t minus 18. And if we factor that, we can see that from negative infinity to 3, v of t is positive. And in other words, the object is moving right. We'll need that in the next question. We really don't care about that yet. And on 3 to infinity, the velocity, oops, sorry, I wrote positive there when it's actually negative. And then when we get bigger than 3, then the velocity is positive. So I said that backwards. Velocity negative means moving left, and then velocity positive means moving right. Sorry about that. And then right away, let's go to acceleration. Acceleration is the derivative of velocity, and a of t is greater than 0 on all real numbers. So the acceleration is always positive. So the only way that we can get opposite signs here, since acceleration is always positive, then we would need velocity to be negative, and that would be on the interval from negative infinity to 3 seconds. And total distance traveled. So here we've already done our hard work here. We know the object changes direction after 3 seconds. So first it was moving left, and then it turns around. So at time 0, it starts out going to the left. At 3 seconds, it turns around and starts going back to the right. So you can either make this little snake-like diagram, or you can just make a chart and say, well, let's find out where it is. We want the end of our interval to be at 5 seconds, so we can find out what its position is, and we would do that using the position function that was given up above. That's 3t squared minus 18t. So you'd have to do a little bit of arithmetic, but we'll come up with 0 and negative 27. These are positions in feet. And then, let's see, how about negative 15 feet? So here we can see that it went backwards 27 feet, and then it went forward 12 feet. So make sure you're using the distance between these. Here it went 27 feet, and from here to here it went 12 feet. So our total distance is 39 feet. So not displacement, not where did it end up, but how far did it travel. So this position was at -15, but the distance between those is what we're looking for. All right, 58, we have a variable in the base and a variable in the exponent. The only way to get that exponent to fall down is to take the natural log of both sides. So we use the fact that the log of a power, the power comes down in front of the log, and that was called logarithmic differentiation. So now we can do the derivative. The derivative of natural log of a glob is 1 over the glob times the chain rule on the glob. You can write dy dx since that's what it's asking for here. Same thing as y prime. And here we have to do a power or a product rule. The first term times the derivative of the second plus the second term times the derivative of the x term is just 1. Those x's cancel. So that will become a 1 plus ln of x. And then what's left to do here is to multiply this y to the other side. Trying to change colors here. So we want to multiply times y. But instead of writing it as y, let's look at our original statement here. We know that y is equivalent to x to the x. So why do we do that? So that we have our function given in terms of the independent variable only. 61 was meant to be a quick and easy related rates question. So when you drop a stone in the water, the ripples of the water start expanding, making circles. So the radius is growing here when we drop this, and we're told that the radius of that circle changes. So the dr dt is what's given, the change in radius with respect to time. So the radius of the circle is growing at 1 foot per second, and we are looking for the area of that circle. How is it changing? So that's what we're looking for. So we need a formula that involves radius and area of a circle. And of course you guys know that is our static formula. So we differentiate with respect to time. Pi is a constant, so we'll just use power rule here. Don't forget the chain rule. Every variable we're differentiating with respect to time. So now we're looking for dA dt, and our specific case here was 3 seconds later. Well, if the radius was growing 1 foot each second, then after 3 seconds, the radius is now 3 feet. And the dr dt is 1 foot per second. Notice that the units even work here if you care to put those in here. This is 3 feet, and the dr dt was 1 foot per second. So we come up with 6 pi square feet per second is our value for dA dt. All right, and in problem 62, the formula for the derivative of arc sine is 1 over the square root of 1 minus the glob squared times the chain rule on the glob. This is the same as 1/4 times x. So the chain rule would be a 1/4. So remember, we don't like complex fractions. We don't like a fraction inside of a fraction. So this term is going to be x squared over 16. So the 1, I'm going to turn the 1 into a 16 over 16 so that I can factor out 1/16. So this is really just arithmetic, guys. The square root of 1/16 is 1/4. So this simplification, and now this 4 will cancel with that 1/4. So this has to be a simpler problem perhaps than you're making it. So we'll have 1 over the square root of 16 minus x squared. And I guess I haven't finished that problem. I guess we were asked to do a numeric derivative. Sorry if I forgot to check that in any previous problem. So we were asked now to take our derivative and to put 1 in there. So maybe I didn't have to be so precise. Could you have substituted way back here? If you're finding a numeric derivative, you didn't need to clean it up algebraically, you could have substituted the arithmetic. All right, but this certainly works. We haven't made any mistakes that I know of. So we're putting 2 in for x here. So we'll get 1 over the square root of 12, 1 over 2 square root of 3. All right, and here we've got some questions. First about the quotient rule, and that's all this is. I suggest that you write carefully what your quotient rule is before you do your substituting of -2. So we have the low function, that's a g of x, times the derivative of the high function, minus the high function, times the derivative of the low function. Stylus is going kind of wacky there. And now we want to put -2 in there, so h prime of 2. So let's read carefully. We want g of 2, so g of positive 2 is 4. So that's going to go in both of these positions. And then we want f prime of -2, f prime of -2. Oh, sorry, let's back up. Did I just put positive 2 in there? Let's back up. This should be -2 here. All the way through, we want to put -2. G of -2. Don't want to make a mistake reading the table. G of -2 should have been a 5. All right, and now we want to do our f prime here of -2. So let's make sure I'm doing this right. F prime of -2 is our value positive 1. And then we want to do our f of -1. Let's see if I can switch colors for this one. F of -2 is 4. And then we want our g prime. Our g prime value of -2 is 3. So I guess we're using everything in that column. So let me check here. So we had a 5 minus a 12. So let me just pause and check my arithmetic. And I think that looks okay. So I guess reading the table carefully would be the lesson here. All right. So now we've got the same type of problem, but we're doing a product rule. So the derivative requires the first term times the derivative of the second, plus the second term times the derivative of the first. And now we want to put 0 in there. So let's make sure that we use the right column this time. So I want to use 0 as my x value. So j prime of 0 would be f of 0. That would be a 5. And a g prime of 0, that would be a 4. Plus a g of 0, that would be a 1. And an f prime of 0 would be a 2. So it looks like we'll have a 22. I don't know if I had paused the recording incorrectly there, so you can read my steps again up above. G of -1 was our value of 2, and then our f prime of 2 was our value of 3, and then our g prime of -1. The g prime of -1 was our value 5, so we came up with a -15 for that chain rule question. All right, and we got one more with that same table, and it has to do with inverses. Well, remember what we know about inverses. The square root of x had the point 42, and its inverse, x squared, has the point 24. So remember that on inverse functions, the x's and the y's swap. So the rise and the run swap. And that means that all we need to do is take the reciprocal. So the problem here, we're looking for m prime of 2, but notice our table has nothing to tell us about m. So we would like to find a point on M where x is equal to 2. So we don't know that, but we do know about its inverse function g. So let's look for a point on g where the y-coordinate is 2. And that's all it amounts to. So the x's and the y's trade places. So look at our g line here, and the y-coordinate is equal to 2 when the x-coordinate is -1. And notice we know what g prime is here. G prime at this point is 5. So if g prime of this point is 5, then we can go back and say, well, then we know that the rise and the run on function m simply flip over. So all we have to do is find the matching point. Slopes on inverses are reciprocals. And we'll finish up 2 more here very quickly. On question 72, when will f be concave up? F will be concave up when f double prime of x is positive. When is f double prime positive? That would be when f prime of x is increasing. So we simply need to find the intervals where this graph, since this is f prime, so where is f prime increasing? So that would be on the interval from -∞ to -1, and the interval from 1 to infinity. And if it's multiple choice, then you would find the place that satisfies that. All right? And then at which values of x will f have a local minimum? So f has a local minimum when f prime of x changes from negative to positive. When a graph is falling and then it rises. So when f prime, this is the graph of f prime. So let's find out here, when does the graph of f prime change from negative to positive? Right here and right here. So that would be at x equals -2 and at x equals +2. All right, enough for one video. Thank you guys very much.